to Virtual Class 6. Today is Tuesday, April 21st. Let's get right to today's top story. Last week I mentioned that the ideal gas law, PV equals nRT, is a simpler version of a more complex equation. I'm going to show you that new equation in a minute, but first let's quickly review the difference between real and ideal gases. As you can see, real gases occupy space. I'm not talking about the space of the container they are in, I'm talking about the volume of the molecules themselves. When we look at molecules, the size of the molecule is negligible in most cases, and the volume we use in the ideal gas equation is close to what it should be. However, with really large molecules, especially large organic molecules, the volume is appreciable, and the results calculated using the simple ideal gas equation are often erroneous. Another aspect of real gases is that they exhibit attractive forces. You might remember back when we were in school talking about different intermolecular forces of attraction like hydrogen bonding and London dispersion forces. Do you remember how London dispersion forces got stronger as the molecules got larger? This was the whole reason a nonpolar molecule like fluorine was a gas, but a much larger nonpolar molecule like iodine, that was a solid. These forces of attraction get stronger as the molecules get larger. So what? Who cares, right? Well, one of the other components in the ideal gas equation is pressure. So think about this for a second. If molecules are attracted to each other, there are going to be fewer interactions of those molecules with the sides of the container. And when they do collide with the side of the container, they're going to be moving slower, thus altering the pressure. Suddenly, the pressure predicted by the ideal gas equation is thrown off once we start talking about larger molecules. So what do scientists do to fix this? Well, the ideal gas equation in its non-simplified form actually looks like this. Notice how the right side of the equation is the same, but the left side of the equation where we find pressure and volume, those look very different. First, let's look at pressure on the left side. I stated earlier that attractive forces decrease the pressure the gas exerts on the side of the container. Therefore, a factor is added to the pressure to correct for the loss in pressure due to those molecular attractions. The value identified as A in the correction factor is specific to the gas you are working with. So if you were to say change from chlorine to fluorine, you would need to look up a different constant to complete your calculation. Now let's look at the volume piece. In the ideal gas equation, the volume is supposed to be the volume of the container. We assume that the volume of the molecules is so small it's negligible. But what if it isn't? What if we are talking about really large molecules? Well then, we would need to subtract out the volume of the molecules themselves to obtain a corrected volume of just the container, the free space that the molecules are permitted to occupy. Notice the constant B used in the correction factor. It is also unique to the specific gas you are talking about. Alright, there are actually published lists of these A and B values that you can look up online. This is a tedious process, and for our purpose, in a high school classroom, let alone one currently being quarantined, the ideal gas equation works just fine. If I were, let's say, an astronaut on a spacecraft launching from Cape Canaveral, I would want to make sure my values are as accurate as possible. Then I would use the corrected form of the equation. In the next segment, we are going to learn how to incorporate density, a topic we learned back in September, with the ideal equation that we learned in our last video. Spoiler alert, like we've experienced in the past, this unit is about to get more challenging. You didn't think for a second that because we are in quarantine that I was going to take it easy on you, right? Okay, so let's look at the density equation first. Hopefully you remember that density is equal to the mass in grams divided by the volume. Well, this still holds true even when we're talking about gases. However, because gas molecules are so far apart from each other, if we continue to use milliliter as the volume unit in our denominator, the density of any gas would begin with a bunch of zeros. So to fix this, scientists examine larger volumes when reporting the density of gases. So instead of using grams per milliliter, we're going to use grams per liter. Great. So now I'm going to throw it over to our in-house scientist, Kevin Orlando, who's going to explain how to incorporate density and the ideal gas law. Take it away. Thanks, Kevin. All right, so let's take a look at the two equations that we have to start off with. First, we have density. Density, remember, is equal to mass divided by volume. And now, instead of having volume in milliliters, we're going to have volume in liters. And our other equation, the ideal gas equation, PV equals nRT. So as I mentioned, volume appears in both equations, but mass doesn't. Or does it? So I want you to think about N, the number of moles, for a minute. N is actually equal to the mass divided by the molar mass, the mass off of the periodic table. This has units of grams for mass, and molar mass has units of grams per mole, and that's why when we divide these, we get units of moles over here. So now, what if I took the moles out of here and substituted in this, mass divided by molar mass? We would have this equation. PV equals mass RT divided by molar mass. Well, that helps because now we have both components that we need for density. So I'm going to rearrange the equation by moving molar mass up here and volume down here. So if I take pressure and I multiply it by molar mass, that will be equal to mass RT divided by volume. Ah, perfect. Because now this looks like this. So my final equation, P times molar mass is equal to density times R times T. And there you have it. If we have our pressure, our molar mass, and our density, we know the value of R, we can find T or whatever other variable we need to solve for. Back to you, Thanks, Kevin. Okay, so there you have it. A new equation that combines density and the ideal gas law. Okay, so now in our final segment, let's try this. We are going to complete a problem using this new equation, and then we are done for today. So I'm going to pass it over to our resident problem solver, Kevin, one last time. Take it away. Thanks, Kevin. Okay, so here is our equation. We have pressure times molar mass is equal to density times our value for R times temperature. So today's question says, what is the density of oxygen gas at a pressure of 780 mmHg and a temperature of 15 degrees Celsius? So let's get all of these variables down. So what is the pressure, molar mass, density, R, and T? So first of all, they give us the pressure as 780.0 mmHg. So I have 780.0. Now, because we're using R, 0.0821 liter ATM over mole Kelvin, we have to have our pressure in units of ATM. We can't have it in mmHg. So we're going to multiply this, 760 mmHg for every 1.00 ATM, and that turns out to be a pressure of 1.03 ATM. Now, the molar mass that we're using is for oxygen. Think, oxygen is not 16, it's a gas, it's 32, it's O2. So the molar mass is 32.00 grams per mole, and remember that's for O2, oxygen gas. They're looking for density, so that's our unknown, and they tell us that the temperature is 15 0.00 degrees Celsius. Of course, we can't use Celsius, so instead we're going to add 273.15 to that. So we're going to get a final temperature that's 288.15 Kelvin. And we can keep both decimal places in this case because this number had 2 decimal places, and this number has 2 decimal places. All right, so let's go back up to our equation. So here's the equation up here. We're going to solve for density. So we're solving for this guy right here. That means R and T have to move down to the other side of the equation. So I'm going to wind up with density equals pressure times molar mass divided by R times T. So my pressure, 1.03 atm. My molar mass, 32.00 grams per mole. Please make sure that you're including units throughout the problem. I see some of you submitting homework assignments without units. That's making me sad. 0.0821 liter atm mole Kelvin. And then finally our temperature, 288.15 Kelvin. Now, this is a units carnival here. So we have atm, that drops out. We have moles down here. Moles drop out. Kelvin on the bottom, Kelvin on top, that drops out. So if you look, the only units that I have left are liters on the bottom, grams on top. That makes sense because we're looking for density, which should have units of grams per liter. Remember, for a gas, we're going to have grams per liter. So we wind up with our final answer. Density is equal to, and we have 3 significant figures here, 3 here, that's kind of our limiting factor. So density equals 1.39 grams per liter. So we had to expect that the problems were going to get a little tougher. They're going to get tougher than this. We're going to keep building one little piece at a time here. So I just want to write down what the homework is for tonight. So again, on the ideal gas law with density, your homework is going to be, again, just 2 problems. So problems 1 and 3. So problem number 1 and problem number 3 for homework tonight. All right, back to you, Kevin. Thanks, Kevin. Okay, there you have it. Please complete homework problems 1 and 3 from the ideal gas law with density problem set. If you have not already submitted the lab, please make sure to do that as soon as possible. And as always, please ask questions using email or message me on Schoology. If you like the videos, please subscribe to my YouTube channel. I hope to see many of you tomorrow on Zoom at either 10 a.m. or 12 p.m. Until then, have a great day, stay healthy. Thanks, everybody.